Welcome back. In this video, we are going to solve example 8.4 that is taken from chapter number 8, Combined Loading, and book name is Mechanics of Material by RC Hibbeler, 9th edition. So statement is the member shown in figure 8.5a has a rectangular cross section. Determine the state of stress at that loading produced at point C. So you can see this is the member that is having pin support at point A, and at point B there is a roller support, and there is a distributed load that is having magnitude 50 kilonewton per meter over a length of 2.5 meter. So the cross section is also shown. This is 50 by 250 millimeter rectangular cross section. So you have to determine the state of stress at point C due to this loading. So let's start with the solution. So first step is that if you remove this pin support at point A, so definitely you will be having a reaction force, horizontal reaction force. Let this is RAX, and similarly you will be having a vertical reaction force that will be equal to RAY. And same is the case when you remove this roller support at point B. So you will be having a reaction force that will be equal to RB. Okay, this will be RB. Now we will find this RAX, RAY, and RB using equation of equilibrium. And you can see this length is 2 meter, and this is 1.5 millimeter. So if I take this angle as theta, so you can say that theta is equal to tangent of theta is equal to perpendicular, which is 1.5 meter, divided by base, that is 2, and theta will be equal to tan inverse 1.5 divided by 2, and when you calculate it you will get this theta will be equal to 36.86 degree. Now we will apply equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So what we will do is that you can see there is a distributed load 50 kilonewton. So when this distributed load is converted into point load, so this will be equal to 50 multiplied by the length over which it acts, that is 2.5. So we will get it 125 kilonewton. Now you can see that this member is making theta degree with the horizontal. Clear? So this will have this. I will resolve this it into rectangular component. This will be its vertical component, and this will be its horizontal component. So you can see this member is making a theta degree with this horizontal. So this line is perpendicular to this, and its vertical line is perpendicular to this. So according to rule, the angle between them is theta. So the angle between these two will be also theta. So I will write here theta as well. So this component will be equal to 125 cos of theta, and this component will be equal to 125 sine of theta. Same is the case for RB. RB will have two components. One component along x direction, that will be this one. This will be equal to RBX, and other component will be vertical component, that will be RBY. So if I draw it like this, now you can see that this RB is perpendicular to this, and this vertical component is perpendicular to this. So if the angle between these two is theta, so this angle will be also theta. So I can write it here as theta. So this component will be equal to RB cos of theta, and this component will be RB sine of theta, this component. Now we have resolved all the forces into its components. So let's apply sum of all moment about point A is equal to 0. So you can see the first force that is producing moment about point A is this RB into perpendicular distance is 6, and that is producing counterclockwise movement. So it will be positive. So I can write it RB multiplied by RB into cos of theta. So theta is 36.86 degree into perpendicular distance is 6. The second moment is produced due to this force, which is again you can see This will be RB into sine of 36.86 and perpendicular distance is 1.5, and this is also producing counterclockwise movement, so it will be positive. So I can write it RB into sine of 36.86 degree multiplied by 1.5. Now the another force that is producing movement is this one, and that is 125 into sine of theta, and theta is again 36.86. Since it is acting at the mid, so this distance will be equal to 1.5 divided by 2, which is 0.75, and this will produce clockwise movement, so it will be negative. So I can write it minus 125 into sine of 36.86 degree multiplied by 0.75, and the last force that is producing movement is this horizontal component, so it will act at this point. So 125 into cos of theta, and perpendicular distance is this one, so this will be half, which is 1 meter plus 4, and that is 5. So it is also producing clockwise, so it will be negative. So I can write it minus 125 into sine of, cos of, not sine, this will be cos of 36.86 degree multiplied by 5 is equal to 0. So this term will give us 4.8 RB. The second term will give us 0.89. The third term will give us minus 500, and fourth term will give us minus 56.23. That will be equal to 0. So it means that 4.8 RB, the second term is 0.89, and there is RB as well. Okay, plus 0.89 RB is equal to 556.23 kilonewton. So I will get 5.69 RB is equal to 556.23, and from here you will get RB will be equal to 97.75 kilonewton. Now we'll find this RAX and RAY by using another equation of equilibrium. So what is that? So I will write it. The equation of equilibrium that we will be using is sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see RAY, which is acting upward. So I will write RAY. This force, you can see this is acting downward. This is 125 cos of theta, and this is upward, plus RB into cos of theta. So I can write it plus, minus 125 into cos of theta is 36.86 degree, plus RB is 97.75 into cos of 36.86 degree is equal to 0. So when you solve this, you will get RAY will be equal to 21.80 kilonewton. Now last unknown reaction force is some RAX. So we will find that by using third equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force toward right side is taken as positive. So you can see RAX is acting positive, minus 125 sine of theta plus this RB sine of theta will be equal to 0. So I will write RAX minus 125 into sine of theta is 36.86 degree, plus RB, which is 97.75 into sine of 36.86 degree is equal to 0. So when you solve this, you will get RAX will be equal to 16.34 kilonewton. Now you have all the reaction forces. So what we will do is that since we are interested to find out the rate of stress at point C, so you will cut the beam at point C and draw the free body diagram. So when you cut it at point C and draw the free body diagram, this is your point A where you have RAX, that is 16.34 kilonewton, and you have RAY, that is 21.80 kilonewton. This is point C. The distance between from A to C is given as 1.5 meter. You can see over here, clear. And when you cut it at point C, so you will be having a shear force V, you will be having a normal force N, and you will be having a moment M. Now we will find this V, M and N by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So 16.34 is toward positive minus this N is negative. Their sum must be equal to 0. So from this we will get N will be equal to 16.34 kilonewton. Okay. Now what we will do is that we will find this shear force by using this equation of equilibrium, and upward force is taken as positive. So N 21.80 is acting upward minus V is acting downward. Their sum must be equal to 0. So from here V will be equal to 21.80 kilonewton. And the last thing is movement. So we will find this movement by using equation of equilibrium, that sum of all movement about point C is equal to 0, taking the counterclockwise movement as positive. So about point C, one movement is due to this load, which is 21.80 into perpendicular distance is 1.5, that is acting clockwise, so it will be negative. Plus there is a reaction moment which is M, their sum must be equal to 0. So I will write plus M minus 21.80 into 1.5 is equal to 0. So from here we will get this moment will be equal to 32.8 kilonewton into meter. Now you have all this shear force, normal force, this is normal force, this is shear force, and this is moment at point C. So what we are going to do is that we will find the normal stresses due to normal force. So I will write it for normal force. First I will write it normal force causes normal stress, clear, and that can be obtained since it is asked to find at C. So sigma C is equal to minus N divided by A. Why minus? Because you can see this N is compressive. This is compressive stress towards C. So I can write it N is minus 16.34 kilonewton. So 3.4 into 10 raised to power 3 divided by area, cross-sectional area. So cross-sectional area is, this is breadth and this is height. So in meter it will be 0.05 and height will be 0.25. So I will write 0.05 multiply by 0.250. Okay. So when you solve this, you will get normal stress will be equal to 1.32 megapascal. That will be negative. But if you remove negative sign, so you can write that this stress is compressive. Okay. Now the second case is that you will have a shear force. So shear force, this vertical shear force causes shear stress, clear, at point C. So we know that shear stress at point C is equal to V into QC divided by I into T, clear. Since QC is equal to Y dash bar into A dash. So what is A dash? So A dash at this point, this is point C. So A dash about this point, there is no area. So it means that A dash is equal to 0. So I can write, since A dash, since for point C A dash is equal to 0, so it means that QC will be equal to 0. And when you put it in this formula, so you will get shear stress at point C will be 0. Okay. Now the third case is that bending moment, this bending moment M. So bending moment M causes bending stresses at C. And this bending stress, which is sigma C, is equal to M into minus M into Y divided by I. Clear? So what is M? M we have already calculated this. So bending stress will be equal to 32.8 into 10 raised to power 3. And what is Y? There is a negative sign. Y is distance from neutral axis. So this is rectangular 250. So its neutral axis, our centroidal axis will be at the half. So this is 125 millimeter. So in meter, this will be equal to 0.125. So Y is equal to C. This is your point C. Clear? So I will write C will be equal to, Y will be equal to 0.125 divided by I. So for rectangular section, it will be equal to 1/12. Breadth is 0.05 and height is 250 millimeter, which is 0.250, and it will be cube. So when you solve this, you will get negative value, and that will be 63.16 megapascal. That will be negative, but if you remove it, negative sign, so it means that bending stress will be compressive. Clear? Now for case 1, if you want to draw the stress distribution, so let me draw it. This is the cross section. For example, if this is the portion of the beam, okay. Now this is your point C. So at point C, due to normal stress, normal force, so the normal force will be like this one. This will be the normal force. So it will be like, the stress distribution will be like this. Since it is compressive, so you can see all the arrowhead will be toward this. So I can write over here that this is for normal stress. Next case is for shear stress. So again, I have to draw the figure like this. Clear? And we know that this is your point C. This is your point C. At C, shear stress will be equal to 0. But when you move downward, the shear stress will be in like this. This will be the shear flow. And we know that shear stress distribution in rectangular section is parabolic in this web portion. So I can say that at point C, the shear stress is 0. But when you move down, shear stress increase and maximum at the centroidal or neutral axis. So this second case is about shear stress distribution in this rectangular section. And the third case is for the bending stress. So how we will do it, that this is its neutral axis. Here, this is the beam. And we know that the above one was in compression. So I can write it like this. This will be the diagram. And below one is in tension. I will also show you how it will be in tension in compression. So you can see that this will be a straight line. Okay. So all stresses will be in compression. And this will be in tension. This is your point C. Okay, so this third case is bending stresses. Now our all all the combinations will give you the state of stress at point C. So you can see I will conclude it over here that we will use superposition, and what superposition says that since shear stress is 0 at point C and normal stress at point C is equal to the combination of this case 1 and 3. Clear? So I can write normal stress at point C is 1.32 megapascal and bending stress at point C is 63.16 megapascal. So total stress at point C is 64.5 megapascal. And this is the answer of our question. So if I want to draw it on the state of element like this, so you can see this will be sigma C. This element is taken at point C. There is sigma C as there is no stress, shear stress at point C. So the stress at point C or state of stress at point C will be represented like this. And this was all about this example 8.4. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching.